Hello and welcome to the second module of this course, Building an AI to Beat the Game Doom. So yes, that's right, we're going to play Doom with an artificial intelligence which will try to kill some monsters to reach some goal in a 3D environment. You know, a 3D map exactly like when you're playing an FPS video game. Only now the difference is, you are not going to play this game, the AI you're going to build and code will be playing it for you. So there we go, we have another very exciting challenge ahead of us. And besides, we're going to take it at the next level now, because we're going to make a more complex model, which is the Deep Convolutional Q-Learning. So I hope after this intuition lectures, you're now very excited to implement it. I am definitely very excited to implement it. So let's start right now. And as you can see, I'm starting with Google because I want to show you the OpenAI Gym environment and walk you through the game we're going to play. That is, of course, Doom. All right, so starting with Google, we're gonna type here OpenAI Gym. So there we go, OpenAI Gym. Then you click on the link and you will find a page, that page. And on the upper left corner of this page, you're gonna click on environments. And that is where you have all the environments, which are actually environments of games. And for each of these games, you can implement an AI to beat the game. And each time it is specified which goal you have to accomplish, what are the actions, and what are the rewards. And know that for most of the games, the input states are actually the input images. That is, it's not like before with the self-driving car where we had, a vector encoding one state of the environment. For most of the games here, the input state is instead the image. So it's exactly like our future AI will have eyes, like us humans do. In fact, this AI we're about to implement is to me the closest to a human brain, because it is going to observe a series of images, then it is going to detect what it has to do in the images, and then using a classic neural network, well, the AI will know which action it should play. And so now let's move on to the game we want to beat, which is the last games on this list, Doom. So let's click on it. And there we go, welcome to the Doom environment. So as you can notice, we have several versions of Doom, and these are just different maps with different levels. So for example, let's have a look at the first one, do basic V0, which is this game that you see here. And as you can see, for this game and for any other games, it is specified the goal. So for this game, the goal is to kill this monster here in 3 seconds with one shot. Then it is specified the rewards. So you get plus 101 points for killing this monster here. Then you get a bad reward with minus 5 points for missing a shot. So actually right now it is getting some bad rewards because it's missing a lot of shots. And you get -1 every 0.020 seconds, 28 seconds. So that's all your rewards. And then you have how the game ends. So it ends when the monster is dead, when the player is dead, or when there is timeout. And you also have the actions. So you have 3 actions for this one. Attack, so that's when you shoot, move right, and move left. Okay, but that's not the Doom game we're going to play. Actually, this one is too simple, that's not my favorite. I prefer the one where we can move forward, move back, turn left, turn right, and shoot many monsters. This one is much more exciting, and actually, this is this one, Doom Corridor V0. So let's click on it. That's the one. So as you can see now, we can actually move forward, we can move left, we can move right, turn left, turn right, and we can shoot again. And we have many more monsters, like these guys here, and our goal, of course, is to not only to shoot them, but that's because the main goal is to reach this tip of the map here, which they call the vest. The goal, the main goal, and that gets us 1000 points, is to reach the vest over there. And to do this, well, we will have to kill the monsters, because if we don't kill the monsters, we will get killed and we will not be able to reach the vest. Alright, and so that's our main goal, reach the vest. Then let's see what our rewards are. We get a first reward when we are getting closer to the vest, so that's plus distance. The reward is exactly the distance we complete while getting closer to the vest. Then minus distance for getting further from the vest, and minus 100 points for getting killed. So here the rewards is just measured with the distance. When you get closer to the vest, you get a reward that is equal to the number of let's say, meters you got closer to this vest. So that's a continuous positive reward. And when you get further from the vest, you get a reward that is equal to the number of meters completed by getting further from this vest. And then if you get killed, you get a bad reward of minus 100 points. Then the game can end when the player touches the vest, so that's when we win. When the player is dead, that's when we lose. And when there is timeout, game over. And here are our allowed actions: attack, shoot, move right, move left, move forward, turn right, and turn left. So we have more actions than before. We now have 6 actions, but that's okay, this will not increase the complexity so bad. Alright, so I hope you're excited with this game. I actually think this is the most exciting game. So we're gonna build an AI to beat that game, and to do this, we will implement a deep convolutional neural network. Hello and welcome again to Module 2 Doom. We will now get us ready to start the implementation of our AI, and as usual, the first thing that we need to do is set the right folder as working directory. So let's do this now so that we can move on to what's more interesting. So as usual, I start on my desktop, then I go to my Artificial Intelligence AZ folder, then Module 2 now, Doom, and there we go, that's the folder we have to set as working directory. So let's do this now. We click on this tool button here, then restart kernel, and then yes. And here we go, we now have the right folder as working directory. So now as you can see, we have 4 files, well actually 3 files in one folder, in this working directory folder. So let's start with the first one. The first one is ai.py. That's of course the file that will contain our artificial intelligence, and that's nothing else than this file here. That is the ai.py file, in which we will implement everything that is related to building an AI, and especially building an AI with the Deep Convolutional Q-Learning model. So basically that's where we'll have the big adventure. Then we have some other files. So we have the second file here, which is experiencereplay.py. And so this time I put experience replay separately, just because we already implemented it, and now we want to focus on what's new. And trust me, we have a lot of new things to do with this new artificial intelligence. Because not only we want to build an AI, but we want to build an AI to beat Doom. So you can imagine that this will require some quite advanced code. So no worries, we have a big code waiting for us, and you will learn a lot of new tricks. That's why this experience replay trick that you already know, and that I remind improves a lot the training, well, let's put it separately in this experiencereplay.py file so that we can now focus on all the new concepts, techniques, and tricks that are waiting for us. Alright, and then we have the image preprocessing.py file. So that's another Python file which will take care of preprocessing our images, because you know this time our AI will have eyes, and that's because the input states are no longer encoded by a vector, but this time the input states are the images. So the first layer of the big neural network that we will make will be the eyes, and that will be the convolutional layers of the convolutional neural network. But to make sure these images can be accepted as input of the convolutional neural network, well, we need to preprocess them. And so this file will take care of preprocessing these images so that they can go into the neural network. And so I separated this file because this is not directly related to AI. And again, we want to keep the maximum of our brain and our memory and our focus on everything that is related to AI. So we are putting this separately so that we can preprocess the images in a flashlight and save some energy for the rest. You can have a look at it if you want. And if you also have the deep learning course, well, you can have a look at the practical tutorials. We talk about image preprocessing, but here again, we really want to focus on AI. Trust me, we have a lot to do. And eventually the last folder, well, that's the videos folder. So right now this folder is empty, as you can see, but when we execute the code, some videos of the AI playing Doom will be added to this folder. So that will be very exciting because we will see on some videos how well the AI is doing. So we will literally see the AI killing the monsters and trying to run towards the goal. So you're gonna see this will be pretty exciting. So of course the first videos will be very bad because the AI will not be trained much yet, and so it will get killed very fast. But then you will see that as the training is progressing, well, the AI will get better and better, and eventually it will manage to kill some monsters, not getting killed, and hopefully we will be able to make it reach the goal. Alright, so let's go back to our AI file, which is this one. And as you can see, I already took care of importing all the essential libraries and packages that we need to play Doom. So let's quickly have a look at them one by one. We have, of course, NumPy, because we'll be working with arrays. That's inevitable. Then we have Torch, of course, because we're implementing the AI with PyTorch. Then we have the torch.nn module, which contains all the tools to implement a neural network. So, for example, the NN module will contain the convolutional layers that will be part of our future neural network. Then we have the nn.functional package, which has the shortcut F, and that contains all the functions that are used in a neural network. So typically the activation functions. We will be using some rectifier activation functions, but also some max pooling function for the convolutional neural network, and all these functions are contained in functional. Then we have Optim, which is of course for our optimizer. I think we will be using an Atom optimizer, and this optimizer is contained in Optim. And then the best of PyTorch, the variable class from the autograd module. And that's all the power of PyTorch, because that's what contains the dynamic graphs, allowing to perform very fast computations of the gradient, even the gradient of composition functions. So we will definitely be using it. As for the self-driving car, but trust me, for Doom, we will be needing it very bad. Okay, so that's all for the essential libraries. Then we need to import some packages related to OpenAI Gym and Doom. So of course we import Gym, then we import some wrappers module of the Gym library, and one of these wrappers is Kip wrapper. So that's basically to import all the tools and environments of Gym. And finally we have this package that we need to import, and which is directly related to Doom, and that's the action space and toDiscrete of the Doom wrapper that basically contains the environment of Doom, and more specifically the actions that can be played, the number of actions for the specific Doom game we're going to play. And I remind that there are 6 actions: move left, move right, turn right, move forward, and shoot, attack. Alright, so that's basically what you need to import for Doom. And then finally, we of course need to import our 2 internal files, experience_replay.py for experience replay, and image preprocessing to preprocess the images that are nothing else than the images of the screen when playing the game, and these images will be preprocessed, converted into NumPy arrays, reshaped to a certain format, and then they will go to the neural network, the convolutional neural network. Alright, so I guess now that we're ready to start the big implementation of this AI, and now it's very important for me to tell you that leads me to the very important point of this module. It's that since I told you we have a big implementation waiting for us, well, in order to not get lost in all this, we need a good structure. And so I already highlighted this structure. We will be implementing this in 2 parts. The first part will be about building the AI. So that's where we will make the brain of the AI. And the brain, as you understood, is nothing else than the neural network. This big CNN composed of some convolutional layers and then some fully connected layers to predict the outputs that are still the Q values. And then we'll make the body of the AI, and that's a new representation I'm bringing to you, and that's again not to get lost. You will see that the further we progress with the code, the more you will see the structure and everything will make sense in the end. And to make sure that makes sense, we need a representation of the AI, and basically this first part, building the AI, will be composed of 3 sections. First section will be about making the brain, that is the neural network. The second section will be about making the body, and I'm calling it the body because this is the part that will tell the AI how to play the action. So first you have the brain that detects the images and predicts the Q values, but then you need to specify how the AI should play the action. And that, it does it with its body, like a human body would do. So the body will be the part where we will specify the method of playing the action. So for example, with our self-driving car, the brain was the neural network we made, and the body was how the action was played, that is, with the softmax method. And here that's the same, we're going to make a brain, and we're going to make a body, which will play the action. I will let you find out, But the key point in all this is that we will have a very structured code so that not only you can take a step back and really understand what's going on, but also you will be able to use it as a framework whenever you want to build an AI for other purposes. Alright, and after building the AI in part 1, we will move on to part 2, which will be about implementing the Deep Convolutional Q-Learning model. And there again, we will have different sections, and one of them will be, of course, to train the AI. So I can't wait to dive into it now. We're going to start with part 1, obviously, and we're going to start by making the brain of our AI. So I can't wait, and until then, enjoy AI. Hello and welcome to the first part of this AI implementation, part 1, building the AI. And as you can see, I already added a dimension in the structure of this implementation with the 3 sections composing part 1, which clearly show how we're going to build this AI. First, we're going to make the brain, that is nothing else than the neural network. Then we're going to make the body, which will define how the actions are going to be played. And then once we have the brain and the body, we will assemble them to make the AI, which will be in the last section of this first part. So now you can already have a good vision of the structure of this implementation. First we make the brain, then we make the body, and then we assemble the two to make the AI. And in this tutorial, we're going to start with the first section that is about making the brain. And this is going to take us 4 tutorials. You can imagine that making a brain is not like making a cake, so this will require more than 1 tutorial. And of course, as usual, we're going to represent that brain with a class because we will need several functions. And in order to have a structure of several functions that will be organized in some kind of instructions, well, of course, we need a class. And that's perfect because once we make that class, well, we will be able to create as many brains as we want by just creating some objects of this class. So again, classes in Python and in general in object-oriented programming languages are very practical because you make your model of something you want to build and then you're able to create as many objects as you want and they will have all the features that you define in the class. And for our brain, the features will be, of course, well, first of all, the architecture of the neural network, which I remind will be a CNN, and of course the different functions like, for example, passing on the signals from the input neurons to the output neurons. So that will be, of course, the forward function that we will make. So let's do this. Let's start making the brain. This is going to be pretty exciting. It is one of my favorite parts, and therefore let's get straight into it. So we're going to start by introducing a class, of course, and we're going to call this class, well, I hesitated to call it brain, but let's be more direct and let's call it CNN, because actually the brain is a CNN network, a convolutional neural network. So as you want, you can call it brain if you want, but at least now we know what we're building. And CNN, as for the network of the self-driving car, is going to inherit from the NN module. So remember, the NN module is what we imported here, and we want to be able to use all the tools of this NN module, and therefore we want to use this technique in object-oriented programming, which is inheritance, and which allows us to, use all the tools from a parent class. And this parent class is going to be nn.module. There we go. And now we can use all the tools and objects of the nn.module. All right? So now that we have our inheritance, we can go into the class to make our first function. And as you probably guess, the first function is the init function. That will define all the variables of the future brain objects, the future CNN objects that will be created. All right, so let's do this. Def, then 2 underscores, init, 2 underscores again, and now we need to input some variables. So first, the first variable is going to be self. That's, of course, to refer to the object. Now I guess you're pretty comfortable with this. Then we're going to add another variable which will be the number of actions in the Doom environment. So we're going to call it number of actions. And actually this variable is not compulsory for the init function. It's just that if you want to test the AI that we're going to build on other Doom environments, well, this will be very practical because we will import this number of actions variable from the Doom environment wrappers with 2 discrete. And when doing that, we will, input the name of the environment, Doom v0, And so if you want to, experiment with this AI on other Doom environments and play on other games, well, you won't have anything to do because this number of actions will directly get the number of actions in the Doom environment you'll be playing with. Okay, so that's it for the two arguments of this init function. So now we can go inside. And now remember what we have to do. The first thing we have to do is activate the inheritance with the super function. So that's exactly like for the self-driving car. We take the super function, then inside we start by inputting the class that will define the neural network, and that is CNN. Then we have to input self to refer to the object, but then remember that's not all. We need to add here a dot, and then the init function with some parentheses. And by doing that, we activate the inheritance, and now we can use all the tools from the nn.module. Alright, so now I think it's time to build the architecture of the neural network. And so as you remember, we're going to build a CNN, a convolutional neural network, simply because this time the AI will have eyes. And the eyes of the AI will be the convolutional layers of this convolutional neural network. And then, after the AI visualizes the images with the convolutional layers, it will pass on the signals into a classic artificial neural network. So that is the one that we had before with fully connected layers. And that's where it will try to predict the Q values for each possible actions that we can play. So you have the architecture in mind. First, we're going to have some convolutional layers and then some fully connected layers. And this will be the brain of our AI. So what we're going to do to, be able to have a step back at what we're making, well, let's just make this architecture with the variables we want to create. So actually, speaking of this architecture, we're going to build a CNN with 3 convolutional layers and then after that, 1 hidden layer. That means that we will need 3 convolutional connections and 2 full connections. And speaking of connections, that's exactly what we're about to define. That will be the variables of our CNN class. And therefore, right now I'm going to define 5 variables, 3 for the convolutional connections and 2 for the full connections. So let's do this. We're going to start with the convolution connections. So I'm going to call them self.convolution1. I'm going to copy that and paste them below. And there we go. Self-convolution 2 and self-convolution 3. That's our convolution connections. So this first convolution 1 here will apply some convolution to the input images to get a first convolutional layer. Then the second convolution 2 here will take the first convolutional layer as input, and by applying again some convolution, it will create a second convolutional layer. And in this convolutional layer, we will get some new images, each of them detecting one specific feature. So we will get these new images in a convolutional layer. Then we will apply this convolution 2 here to connect these new images from this first convolutional layer to some new images of a second convolutional layer. And these new images again will detect some features in the images of the first convolutional layer. So it's just to reinforce the feature detection. And then to the images of the second convolutional layer, we apply the third convolution here to get, for each of them, some more images that detect even more features inside the input images. And so the more we do this, the more we apply some convolutions to the different layers of images, well, the more we are able to detect some features. And that's how, by detecting the features, the AI will understand where the monsters are, where it has to shoot to kill them, and where it should go to. It will also detect the walls, the obstacles, well, literally where it has to go. And that is thanks to what all these convolutional layers detect in the original input images. Alright, so that's for the convolution part of the CNN. But then remember, after the convolutional layers, we have to flatten all the pixels obtained by the different series of convolutions that were applied. And by flattening all the arrays of pixels, we get this huge vector that will become the input of a classic artificial neural network. And that's where we get our fully connected layers and therefore our full connections. And so now what we have to do is create 2 new variables because we're going to have 1 hidden layer in this classic artificial neural network that comes next. And therefore we need 1 full connection from this huge flattened vector to this 1 hidden layer. and a second full connection between this one hidden layer and the output layer composed of the output neurons that are the Q values. So let's make these two first connections and then we will define all these connections. So as for the self-driving car, we're going to call them self.fc1 and then self.fc2. Alright, so now we have all our variables, and so now what we have to do is, of course, define them with the classes of the NN module. So that means we will basically create the architecture of the neural network, and that's what we'll do in the next tutorial. Until then, enjoy AI! Hello and welcome to this Python tutorial. Now we have to define the 5 variables of this init function, that is, the 3 convolutions and the 2 full connections. So let's start with the first one. Convolution 1 applies convolution to the input images, so that's the original images. And now you're going to see how everything will become so simple. To create this convolution, well, what we have to do is actually create an object of some specific class, and this class is taken from NN, and then the class is conv2d. 2D because we're working with 2D images. And now, as you can see, we need to input several arguments. First one is in channels, so let's input it, in channels. The second one is out channels. The third one is kernel size, and the rest of them are the stride, the padding, the dilation, groups, and bias. And we have default values for all these ones, so we're not going to input them, we're going to keep the default values. But what's important is these 3 arguments, in channels, out channels, and kernel size. And so do you guess what they correspond to? Well, very simply, in channels correspond to the input of the convolution, and out channels correspond to the output of the convolution. So in channels, what is it going to be? Well, very simply, that's going to be the number of channels in our images. And actually, we're going to work with black and white images, because basically we don't need colors to recognize the monsters. The AI is totally capable of recognizing the monsters in black and white, so we don't need the colors. It will just recognize them by their shape. And therefore, we're going to use 1 channel. So 1 channel is when you have black and white images, and 3 channels is when you have colored images. And therefore, since we're working with black and white images, in channels is going to be equal to 1. Then out channels. So out channels is going to be equal to the images you want to have in the convolutional layer, which is the output of this convolution 1. And so basically, this is equal to the number of features you want to detect in your original images. Because we will create 1 image per feature we want to detect, because basically you know how it works. We apply 1 feature detector to the input image to detect a specific feature in the input image, and therefore the number of output images here is the number of features we want to detect. So now the question is, how many features do we want to detect? Well, a common practice is to start with 32 feature detectors. And so that will lead us to 32 processed images in this first convolutional layer. So the input is 1 black and white image, a real image, and the output in the first convolutional layer is 32 processed images. And by processed, I mean, of course, that the convolution was applied to the input image to get 32 new images with detected features. And then we need to specify a kernel size, which is nothing else than the dimensions of this square that will go through the original image. And in common practice, we use either 2x2 or 3x3 or 5x5. And for the first one, we're going to use a 5x5 feature detector. That is a feature detector that will have 5x5 dimensions. And then we will reduce the size of this kernel for the next convolutional layers. And speaking of it, this is exactly what we're going to do now. We are going to copy this to define the second convolution, and therefore I'm pasting that here. And now it's very funny and very easy. It's like a domino. The input channel of the second convolutional layer is the output channel of the first convolutional layer. So this number of outputs 32 here is the same number of inputs 32 here. And that's because we have 32 images in the input convolutional layer of this second convolution. And so this second convolution is applied to this second convolutional layer to return a third convolutional layer. And so now the question is, how many new images do we want? Well, same, let's create 32 new images. 32 is actually a very common number in convolutional neural networks. If you look at the architectures, you will find 32 in many of them. And then for the kernel size, well, we need to reduce the kernel size, that is the dimensions of our feature detector. And so now we're going to go from 5 to either 4 or even 3. And then we'll go even smaller. All right, so our second convolution is ready. It takes as input 32 processed images, each one detecting a first feature of the original input image, and it creates 32 new images thanks to this reduced dimensions of the feature detector. And so now let's push this even more. So I'm copying this and pasting that here to create a third convolution to detect some features. And so now that's the same. The input channels here is the number of input images at the left of the convolution connection, and that is the number of processed images that was at the right of the previous convolution connection, so that's 32, therefore we keep 32 here, that's perfect. And now the question is again, how many new images do we want to detect? We are going to take now 64, and therefore 64 output processed images, and of course now we take a smaller kernel size, and we're going to take 2. And so that's a very classic architecture of a convolutional layer, and it's very efficient to have a high level of feature detection inside images. All right, and so now that we have our 3 convolutional layers, thanks to our 3 convolution connections here, well, now it's time to get our 2 full connections that I remind will take this huge vector that we obtain after flattening all the 64 times 32 times 32 again images that we got from all these convolutions. So we flatten all the pixels of these images and we get one huge vector that will become the input of a new fully connected neural network. And so that's when we have to make these full connections between first this huge vector and a hidden layer, and then a second full connection between the hidden layer and the output layer composed of the output neurons, each one corresponding to a Q value of the possible actions. So let's make these 2 full connections. You know how to do that. That's exactly what we did for the self-driving car. So let's do that again. Well, first we take our NN module, then we take the linear class, because again, the full connection we create is an object of the linear class. And then in parentheses, well, that's the same. First we input the input features, that is the number of them, then the output features. And so the input features for the first full connection, what is it going to be? Well, that's going to be equal to the number of pixels there are in this huge vector obtained after flattening all the processed images after the 3 convolutions. And so what is this number? Well, actually there is a trick here. This number is actually hard to get. We actually need to make a function to compute that number. We don't have a variable that will get us this number. We have to compute it. And therefore, what we're going to do now, and now it's very important to understand the mindset of programming that we must have. I'm trying to bring to you the mindset that is what you must be thinking right now to do to overcome this obstacle, because the first time you might say, hey, I don't have this number of neurons in the flattened vector. What should I do? I'm stuck here. Well, no, actually, because what you can do now is simply input any name here that will represent this number of neurons. So I'm calling it number neurons, number of neurons. And then we will simply make a function that will return in this number of neurons variable this number of pixels we're looking for. So we can totally do that. We can totally put this variable. Well, of course, we'll get a warning because it doesn't exist yet, but we will create it afterwards with the function. And we are totally allowed to do that even if the function comes afterwards. So that's a typical programming thinking you must have when you get that kind of obstacle. Well, you can make a function to get what you're missing. All right, and then out features, and out features, that's the number of neurons in the hidden layer, and that, this time, is up to you. That depends on the architecture of the neural network you want to create. And so a good number would be not a too small number. So for example, 40 neurons might be fine. We can try to increase it. If the training is not too slow, you can try to increase it. Maybe that will improve the predictions. But let's start with 40. Maybe we'll increase that afterwards. All right, so that's it for the first full connection. Then we'll copy this, paste that here for the second full connection. That is the connection between the hidden layer and the output layer. And so the in features here becomes the out features of the previous layer, and that is 40. So here we input 40. That's of course the number of neurons in the hidden layer. And out features here is going to be equal to the number of output neurons there should be in our neural network. And since each output neuron corresponds to one Q value, and one Q value corresponds to one action, well, the number of output neurons here is, of course, the number of actions. And we have one variable for this, which is number actions, and therefore, here we input number actions. And there we go, congratulations, we defined the architecture of our neural network. Our neural network is composed of 3 convolutional layers and 1 hidden layer, all this in one big CNN. And this CNN will detect the features in the game so that the AI will know what it has to do, where it has to go, and where it needs to shoot. So there we go for this step. That's the first very important step done. Now we're going to move on to the next step, which is of course to get this number of neurons that is still missing. That's actually why we have the warning here, undefined name, number neurons. But no worries, now we will make a function that will return the number of neurons in this huge vector, and we will put that number in a variable that we'll call number neurons. So let's do this in the next tutorial. That's our next step, and until then, enjoy AI. Hello and welcome to this Python tutorial. So now the next step is to make that count neurons function, which will give us what we want, that is this number of neurons in this huge vector after the convolutions are applied. That's the only missing information we need right now, and we're going to get it with a function. So let's make this function. We are going to call it count underscore neurons, very simply. And what is this count neurons function going to take as arguments? Well, it is going to take the object, self, but then it's going to take something else. Because this number of output neurons in the flattening layer actually only depends on one thing. It depends on the dimensions of the original input image, the one that goes at the very beginning of the neural network. And so the only argument we need right now is actually these dimensions, the dimensions of the input images. Therefore, let's give a name to this argument representing the dimensions of the input image, and we're going to call it image dim. All right, and I can tell you right now that the actual dimensions of the input images coming from Doom are going to be 80 by 80. We're going to reduce the size of the original images to 80 by 80, and that's going to be the format of the images going into the neural network. So image dim is actually going to be 18080, and the 1 corresponds to the fact that we're working with black and white images, that is with only one channel. So image dim is going to be equal later to the tuple 180 and 80. Alright, so that's the only argument we need, and now let's count the neurons. So how are we going to do that? Well, first of all, we actually don't have any input image right now. We don't have any Doom image that we can import. We're going to do that later. So the first thing we have to do is create a fake image, but that has the dimensions 80 by 80. We're going to create that fake image with fake pixels, and that will still give us eventually the number that we want, because that number only depends on the dimensions and not on the pixels that are inside the images. So let's just create a fake image to start, and then we will compute the number of neurons that we want. So the trick to create a fake image is, well, we're going to call it x, first of all, and then we're going to use the torch.rand, because, we're going to put some random pixels in these images, so we're using this random functions from torch, which is the rand function. Then inside, we're going to input, as you can see, the dimensions of the images, that is 18080. But since we're going to input this image into the neural network, and as you remember, the neural network can only accept batches of input states, that is here batches of input images, we are going to create that fake dimension, which we can directly do in this rand function. We actually just need to start with a 1, that will correspond to the batch, and then we can just put the tuple 18080 corresponding to the dimensions of the input image. And as you understood, these dimensions are contained in this image dim argument, which represents that tuple 18080. So now we just need to add image dim. But in order to pass the elements of a tuple, because right now image dim is a tuple, as a list of arguments of a function, we need to add here before image dim, that is before the tuple, a star. The star will allow to pass the elements of the image dim tuple as a list of arguments for a function. And as you can see, that's exactly what is specified here with the star and the dimensions. Alright, so that will create an image of fake pixels. So that will have nothing to do with the Doom images, but again, we will still be able to get the final number of neurons. And now the last thing that we need to do, remember, is to convert this input batch vector into a torch variable, because this is going to go into the neural network. Alright, so this now represents an input image of random pixels that was just converted into a torch variable, and that will now go into the neural network, and more specifically, the convolutional layers of the neural network. Because since we only need the number of neurons after the convolutions are applied, we will just go up to the convolution 3, so right after the third convolutional layer, and we will not go into the 2 full connections here. And that's because the number of neurons that we want is between convolution 3 and FC1. Alright, so now that we have one input image with the right dimensions, well, it's time to propagate this image into the neural network to reach the flattening layer. And then we're going to get the neurons in the flattening layer, and we will just get the information that we want, that is, the number of neurons in this flattening layer. So now what we have to do is exactly what we do in a forward function. We need to propagate the signals into the neural network, but only in the convolutional layers until we reach the flattening layer. So let's do this. We're going to update x. Now x is the input image, and with this second x here, x will become, well, the first convolutional layer. And now what we have to do is a 3 steps process. First step, we apply the convolution to the input images. Then second step, we apply max pooling to the obtained convoluted images. And then third step, we activate the neurons in this pooled convoluted images. And so x will become this first convolutional layer composed of all these pooled convoluted images. So let's do this. First step, apply the first convolution, convolution 1, to the input images. So what we do is take our convolution 1, self.convolution1, there we go. We apply it to our input images, which so far are represented by x. So that's the first step. First step done. Now, second step, we are going to apply max pooling to our convoluted images, returned by convolution 1x. And to apply max pooling, well, we're going to take a function from the functional module. So we take f, the shortcut, then dot, and then we're going to use the function max pool 2d. That's the one. We put self-convolution 1x in the parenthesis of the max pool 2d function, because we apply max pooling to the convoluted images. But this max pooling function takes additional arguments, which are first the kernel size. So again, that's the size of the window sliding through your images, and that will take the maximum of the pixels in each slide. So that will still detect the features, because the features are associated to a high value of the pixel in the arrays, as you saw in the intuition lectures. So this first argument here we need to input is this kernel size, and we're going to take 3. That's a common choice for the kernel size. And then we need to input the strides, by how many pixels it's going to slide in the images. And we're going to take a stride of 2. Again, that's a common choice. So there we go. Now the second step is done. And now let's move on to the third step, which is to activate all the neurons in this pooled and convoluted images in this first convolutional layer. And to do this, again, we are going to apply a function to all this. And so here I'm taking f again, because we're going to take another function, which, as you might have guessed, is going to be an activation function. But which one? As usual, it's going to be a rectifier activation function. And maybe you remember the name for that is relu. There we go, that's the one. And so we apply relu to our pooled convoluted images, that is all this. All right, and that's it. 3 steps done. That was very quick. So remember, the way we have to look at this is first we apply the convolution to our input images. Then we apply max pooling to our convoluted images obtained with the convolution. And then we activate the neurons in all this pooled convolutional layer with the rectifier activation function. So perfect. We get our first convolutional layer on which was applied max pooling and in which the neurons are now activated. And so basically what it does is that it propagates the signals from the first convolutional layer to the next one. And speaking of the next one, that's exactly what we're going to take care of right now. We are going to do the same thing as we just did on the first convolutional layer to the second convolutional layer to again propagate the signals further into the neural network by activating the neurons of the second convolutional layer. But before doing this, we need to get this convolutional layer, and so we are going to apply convolution 2 to x, that is now the first convolutional layer, while we are going to apply convolution 2 to x to obtain the second convolutional layer, after which we will be max pooling it, and then finally activating its neurons. So let's do this. It's actually very easy. We just need to copy that and pasting that below. Now, of course, we need to replace convolution 1 by convolution 2. And there we go. That's actually ready. See? Very easy. And so now with this line, we propagate the signals from the second convolutional layer to the next one, which is going to be the third convolutional layer. And to get this third convolutional layer, well, we need to apply that again. So I'm copying this, pasting that below, and replacing convolution 2 by convolution 3. And that's done. Isn't it so practical? We propagate the signals in the 3 convolutional layers in a flashlight thanks to this awesome structure. Alright, so perfect. Now we have our signals propagated up to the third convolutional layer and after. And speaking of after, that leads us to what we're looking for, what we're interested in, that is the flattening layer. Alright, so now that we have our third convolutional layer, that's the last x here, it's time to get our flattening layer. And so that's exactly what we're going to do now. We're going to flatten all the pixels of this third convolutional layer. That is, we're going to take all the pixels of all the channels of the third convolutional layer. We're going to put them one after the other in a huge vector. And of course, this huge vector is going to be nothing else than the flattening layer. And at the same time, we will use a trick to get the number of neurons in this flattening layer. That's exactly what we're looking for. That's the number of neurons we're missing. And therefore, let's directly return what we want. And in this return, we're going to flatten the third convolutional layer and get at the same time the number of neurons in this flattening layer. So we're going to take x, which is our third convolutional layer. We're going to take all the channels of this third convolutional layer, and we're going to use a function, which is the size function, to flatten all the pixels of all these channels in one same huge vector. And so the trick, you can find it in the PyTorch tutorial. Well, first we take the data of x, because x is a special structure. You know, it's a torch variable, so it has a pretty complex structure. But first we need to access it with data here. Then we need to view what's inside of it. So we use this view function. And now we need to access what we're looking for, and that is given with the arguments 1 and -1. You don't have to understand what's inside the structure, but you can just understand that this is how we're going to get this number of neurons. And then to finish, we need to add size, then parenthesis, and inside we input 1. So basically what we do here, what we do is we take all the pixels of all the channels and we put them one after the other in this huge vector, which will be the input of the fully connected network. That's basically what this size one does, and with this we can get this number of neurons that we're looking for. Alright, so now we get what we want, and so finally we can replace number neurons here by what is returned by this function when it is applied to the format of the DOOM images, that is 1 by 80 by 80. So what we have to do now is replace number neurons by, we take the count neurons function, which we apply to the format of the DOOM images, which will be the tuple 1, 80, and 80. And there we go. And of course, we don't forget self, because count neuron is actually a method of the CNN class. So we need to add the self, and now the warning should disappear. And there we go. Now everything is good. We get the architecture of the neural network with nothing missing, and we have this count neurons function in case you want to try some other architectures and you don't want to count this number of neurons manually. You just use this function, you apply it to the format of your images, And this will get you directly what you want, that is the number of neurons in the flattening layer, without having to do anything and whatever the architecture is. So that's pretty cool. And now we're done with the first big important step of this brain that we're making. And we have one last step, that is one last function to make, which is going to be the main forward function. So we're going to propagate the signals from the beginning of the brain, that is from the eyes of the AI, up to the output layer, that is after the second full connection. So we'll do that in the next tutorial, and until then, enjoy AI! Hello and welcome to the last step of our process to make the brain. We have one function to make left. This is the forward function that will propagate the signals in all the layers of the neural network, including the 3 convolutional layers and the fully connected layer. And so this function is the forward function, exactly like for the self-driving car, except this time we have to propagate the signals in the convolutional layers before the fully connected layer. And the good news is we already did that in the previous step with the count neurons function. So we already have the code to propagate the signal in the convolutional layers. And so this will be very quick. We will just combine what we did here and what we did for the self-driving car, and we'll get our forward function for our brain. So let's do this. We introduce a new function here, the last one for the brain. And this function is the forward function, which takes as argument, well, exactly like before, self, to refer to the object, and x, which will be first the input images, and then x will be updated as the signal is propagated into the neural network. All right, so colon, and then let's go inside the function. So as I just said, we already made the code to propagate the signals in the 3 convolutional layers. That's exactly these 3 lines of code. So I'm copying them and pasting them here, and there we go. We already have our propagation of the signal in the 3 convolutional layers. And so now we just need to propagate the signal from the convolutional layers to the hidden layer, and then eventually to the output layer that is at the very end of the neural network. And to do this, we first need to flatten the 3rd convolutional layer that we obtained here. Remember, x at first is the input image, then here x becomes the 1st convolutional layer, then here x becomes the 2nd convolutional layer, and then here x becomes the 3rd convolutional layer. So right now at this stage, x is the 3rd convolutional layer, and now to obtain the flattening layer, we need to flatten this 3rd convolutional layer x. And to do this, we're going to do something quite similar as we did here, only this time we don't need the number of neurons. We simply need to flatten the channels in the 3rd convolutional layer. So this will be quite more simple, but very similar. And to do this, well, we're going to take x again, because x is going to become the flattening layer. So we're just updating x. So x equal, then we take x again, but this x is the old x, that is the 3rd convolutional layer. So we take the 3rd convolutional layer, then dot. Then we take the view function, to which we apply 2 arguments. The first one is x.size0. So again, we take the size function to take all the pixels of all the in the 3rd convolutional layer, and we put them one after the other in this huge vector that is going to become this x here. And this x then will become the input of the fully connected network. But that's not all. We need to add here comma and -1. So that trick, you can find it in the PyTorch tutorials. That's how you can flatten a convolutional layer composed of several channels by using the size function. And of course, if you want more details on how this works, you can go to the PyTorch tutorials. I will provide the link. So now that we got our flattening layer, well, this flattening layer is going to become the input of a classic fully connected network with a simple linear transmission of the signal. And so now we're not going to use a convolution function to pass on the signal. We're going to use a linear transmission with the linear class. And then to break the linearity, because we're working with images and images have nonlinear relationships, well, we're going to use a rectifier function to be able to learn these nonlinear relationships. So let's do this. This is actually the next step. And so now that's exactly like what we did for the self-driving car. We take x because we want to update it again. We want to get the hidden layer now. And so first what we do is we take our full connection FC1, because the full connection FC1 is the one that connects the flattening layer to the hidden layer, and therefore we need to take FC1 and apply it to the X that we have right now, which is the flattening layer. And we don't forget the self, of course, because FC1 is a variable of our init function. So self.fc1x, and so that passes on linearly the signal from the flattening layer to the hidden layer. But now we need to activate these neurons while at the same time breaking the linearity, and that's exactly what we do with the rectifier activation function. So now what we have to do is take our functional module, and from this functional module we take, of course, our rectifier function, that is the ReLU, and we put self.fc1 inside the parentheses. Alright, so what happens in this line of code is that first we propagate the signals from the flattening layer to the hidden layer of the fully connected network, and then we activate the neurons of this hidden layer by breaking the linearity with this rectifier activation function. And we get our hidden layer, that is X here. Perfect, and now we have one last step to do. It is of course to propagate the signal from the hidden layer to the output layer with the final output neurons. And to do this, well, that's very simple. That's exactly like what we did for the self-driving car. We take our second full connection, FC2, and we apply it to, of course, the neurons of the hidden layer, that is right now X. So X here is the neurons of the hidden layer, this old X, and X here becomes, of course, the output neurons of the output layer containing the Q values. And finally, we simply return the output neurons, that is X, with the Q values. So perfect, congratulations, we just made a brain. We just made the brain of our AI with the eyes and the rest of the cells. So congratulations, now it's time to make the body, that is defining how we're going to play the action after all the signals are processed in the brain. So that's our second big step. Let's do this in the next tutorials, and until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so we just made the brain and now let's make the body. So as you understood, the body is the part where we define how the actions are going to be played, like what happens for a real human body. You know, you have the brain that sends the signals to the body and then your body plays the action. Well, here that's the same. We have our signals coming from the brain. We get the output signal with the forward function here. You know, first what happens is that we get the images. The images go into the eyes of the neural network, composed of the 3 convolutional layers, and then with the fully connected layers, we get the output signal from the brain, which contains the Q values. But then, this output signal should be forwarded to the body, and the body will play the action. And so that's exactly the part that we're going to take care of right now. We're going to implement the way the body will play the action. And the way it will do it is with a softmax method, exactly like for the self-driving car. I insist that the softmax method is highly recommended for playing an action with the body of the AI, and therefore that's the one we're going to go for. But as opposed to the self-driving car, we're going to make a class, and this class will of course correspond to the body of the AI, and therefore let's start by introducing a class here that we're going to call softmax body, like this. I don't want to call it softmax only because softmax is a class of PyTorch from the NN module, so it's dangerous to call it this way. Therefore, I'm calling it softmax body, and now it's very clear that our CNN, convolutional neural network, is the brain, and softmax body is the body of the AI. So softmax body, and let's inherit from the nn.module. I don't think we're going to use it, but anyway, we can still inherit from it. You know, in case you want to improve the softmax body class and want to use some tools from the NN module, well, you will be able to do it with the NN module. But at this point, I don't think we will be using any of the NN module. So then colon, and let's go inside the body. All right, so first, as usual, we're going to start with our init function to define the variables of the future body objects, that is the bodies of the AI. And actually, as for a human body, a parameter that can define it is the temperature. And actually, that's going to be the only temperature. So it's a simple body, but still, using this temperature parameter will do a lot for us. Okay, but before the temperature, let's not forget the self for the objects, for the bodies. And now we can input the temperature, T, which is the same parameter as the one we use for the self-driving car. Okay, and then colon, and let's define our variables. So, since we inherit from the NN module, we're going to use the super function again. And so let's be efficient. Let's copy this and let's paste that right here. And of course, let's not forget to replace CNN here by soft max body. There you go. Now I suppose that might become a reflex for you to use the super function at this stage. And then what we have to do is, of course, set our temperature variable with self.t, and that will be equal to the argument that will be input when creating an object of the softMaxBody class. I remind that whenever you create an object of the softMaxBody class, you have to input the arguments that are in the init function, and therefore that is t. And then the variable of your object attached to your object self.t will be equal to this t, which is the argument that you will input. Alright, and now that's it for the init function. That's actually all we need. So I guess we're ready to move on to the next function of the softMaxBody class, and this is going to be the last function. There are only two functions, the init function and the next one that we will implement in the next tutorial, which will be the forward function. And why forward? That's because right now we have to forward the output signal from the brain, that is, the Q values contained in the output neurons of the output layer, to the body, which will play the action. So we are forwarding the output signal from the brain to the body that will play the action. Move forward, go left, go right, turn left, turn right, or shoot. Alright, so let's do that in the next tutorial, and until then, enjoy AI. Hello and welcome to this Python tutorial. Alright, so now we're going to make the forward function, which will propagate the output signals of our brain to the body of the AI so that it will play the right action to reach the vest. But there is no right action yet because there is no training yet. We have not trained the AI yet, but this is exactly what we will do in part 2, implementing Deep Convolutional Q-Learning, which, by the way, I will rename Training the AI with Deep Convolutional Q-Learning. But right now we need to forward the signal from the output layer of the brain to the body, and that's exactly what we're going to do with this forward function, which is the last function of our body. So let's do this. We start with def forward, and according to you, what argument is it going to take? Well, it's going to take, of course, first self, and then, is there another one? Well, yes, there is. And what is it going to be? Well, very naturally, we want to forward the output signal of the brain to the body, and therefore the input will be the output signal of the brain. And so now we need to give a name to these output signals. And so I'm going to add here the argument output. Alright, so that corresponds to the output signals of the brain after the input images are propagated through all the brain to reach the output layer, which is x here, returned by the forward function of the brain. And now this output signal of the brain will be forwarded to the body with this new forward function that we make in the softMaxBody class. So let's do this. Let's add some colon here. And now, as you understood, we're going to use a softmax method to play the action. That means that the body of our AI, after receiving the output signals of the brain, will play the actions with the softmax technique. So basically now what we have to do is exactly the same as what we did for the self-driving car. We're going to get our distribution of probabilities. That's the first step. And then we're going to sample an action according to this distribution of probabilities. So basically what we could do now is get our self-driving car file and copy-paste what we implemented for the select action function in the self-driving car. But let's do it again. It will be good practice, and actually you can try to type it before me. Okay, so first what we're going to do is get our probabilities. So I remind this is a distribution of probabilities for each of the Q values, which depend on the input image and each action. So we have one Q value for each of the 6 or 7 possible actions, and therefore we get a distribution of 7 probabilities. I'm saying 7 because I think there are 7 actions instead of 6, because besides moving forward, left, right, or shooting, we can also run. So that makes 7 possible actions, and therefore we get a distribution of 7 probabilities, one for each Q value associated to each action. So probs equals, and now remember what we have to do? Well, basically we have to use the softmax function from the functional module. So that's very simple. We take our functional module first, then dot, and then we take our softmax function, here it is, we press enter, and now we input the arguments of the softmax function, which I remind are the elements for which you want to create a distribution of probabilities. And so that's of course the Q values, that is the outputs of the neural network. That's the outputs of the neural network for which you want to create a distribution of probabilities. And I remind that we want to create this distribution of probabilities to be able to explore the different actions instead of directly picking the one that has the maximum Q value. If we directly pick the one that has the maximum Q value, well, we don't explore much the other actions and we might miss something. But with this softmax method, we can do some more exploration and therefore maybe find some hidden solutions in the patterns that might be much better. So again, I highly recommend softmax, and therefore now what we have to do is input the Q values, that is our outputs here, the outputs of our brain. So outputs, there we go. But then we have this temperature parameter that we can use, that we can configure to customize the exploration. Remember that the higher we set the temperature, the less exploration of the other actions we will do, because the best action will be selected with a higher probability, as opposed to the other actions which will be selected with lower probabilities. So that's exactly like for the self-driving car, and therefore we have to multiply the outputs here by our temperature parameter, self.t. There we go. Perfect. Now we get a little warning because we haven't used props yet, but we're about to use it now. And so that brings us to the next thing we have to do. How are we going to use these probabilities? Well, we're going to sample the final action to play from this distribution of probabilities. And therefore, what we have to do now is use the multinomial function to sample the action according to this distribution of probabilities. So now we're ready to get our actions. So I'm creating a new variable here because that will become the actions that will be played by the body of our AI. And so now we take our distribution of probabilities, probs, to which we add dot and then the multinomial method. All right, and now we get our final actions to play. They're sampled from our props distribution. Okay, perfect. So now we're ready to return what we want, that is the actions to play. And these are, of course, actions. And now the warning should disappear. We use everything we want. There we go. Perfect. So now the forward function is ready, and congratulations, the body is also ready. So now we have our brain, we have our body, and therefore we're ready to assemble them to make the future AI. Our future AI will be composed of nothing else than a brain and a body, and so it will have intelligence and a body to play the actions, which will be the right actions to play thanks to its intelligence. But remember, before we have to train its intelligence, and that's what we'll do in part 2, training the AI with Deep Convolutional Q-Learning. Alright, so let's make the AI in the next tutorials. It's again going to be a class of 2 functions, I think, and so this will require 2 or 3 tutorials. So I can't wait, this will be exciting, and until then, enjoy AI! Hello and welcome to this tutorial. So now that we have a brain and a body, we can make the AI. Of course, we're going to assemble them, and you're going to see how now things are all going to make sense. You're going to understand why we had to make some classes, or more specifically the purpose of making these classes, and mostly you're going to get the intuitive sense of how you can play with objects to create new objects, bigger objects. And as you understood, we already created 2 classes, the brain and the body. So then by creating some objects of these 2 classes, well, we can make a bigger object, which will be the AI. And that's exactly what we're going to do now. We're going to make the AI by assembling the 2 classes that we created, that is the brain and the body. So let's do this. It's going to become super intuitive now. I'm going to introduce a new class, which of course I'm going to call AI, because now we're ready to make the final AI. And right here, I'm going to start with the init function. And what is this init function going to take? It is right now that things will make a lot of sense. Well, first we get the inevitable self for the object, but then the 2 arguments are going to be nothing else than a brain and a body. That's the 2 elements that we need to build an AI. We need a brain, the neural network, and a body, which will play the action with softmax. And so now, very simply, what we have to do is defining the variables of our AI object, because right now brain and body are just arguments. So let's do this. We have to make two variables, obviously. The first one is self.brain, which will be equal to the brain argument, but which later will be a brain object created from this CNN class. And then the second variable is self.body, which will be equal to the body argument right here, but which in the future will be, of course, an object of this softmax body class. And so now, as simple as that, thanks to this pretty awesome structure that we made here, we build an AI. Not trained yet, not intelligent yet, but still we have a brain and a body. So that's perfect. And now the only thing that we have to do left is make a big forward function that will do the whole propagation. You know, since now our AI is assembled, well, we're not going to use separately the two forward functions, you know, the one of the brain and the one of the body. We're going to make a big forward function, which will be our next function, which will take the images as input, then we'll propagate the signals in the brain, and for this we will of course use the first forward function, and then once we get the output signals of the brain, we will forward these output signals into the body, with the forward function here that will use a softmax technique. And then eventually, we will return the actions to play. And it is just now that we can make this big forward function because we have assembled the brain and the body. And so we're not going to call this next function forward, we're going to use the call function, which is kind of like the init function, but that will call the two forward functions here from the brain and the body to propagate the signal from the very beginning with the input images to the very end with the action to play. And that's why the next function we will make now is this call function that will combine the two forward functions of the brain and the body. That's the only thing we have to do, and then we will have our AI ready. So let's make this final step in the next tutorial, and until then, enjoy AI! Hello and welcome to the very last step of this part 1, building the AI. Now the only thing that we have to do left is to make this big forward function that will propagate the signal from the very beginning when the brain is getting the image to the very end when the AI plays the action. So we're going to make this whole function, and that's going to be our last step before we move on to part 2, training our AI with Deep Convolutional Q-Learning. So let's do this. We are going to take the function call, which actually is similar to the init function. That is, it's an existing function, but this time we use it to call some other functions, the ones that we made before. Because you know we're going to use the forward function from the brain and the forward function from the body. And so we're using this call function now to basically call these functions. So call is going to take two arguments. The first one is self, of course, the object, and a second argument, which according to you, what is it going to be? Well, we're doing the whole propagation this time. So what we want to take as input is of course the input images, because of course that's the starting point when the AI is playing the game. It is first visualizing the images of the game, then propagates the signals in the brain, and then plays the action. Therefore, the second argument is going to be input. And now we are ready to make this whole propagation. So let's do this. Okay, so the first step, what is it? The first step is receiving the input images from the game. And since these images are going to enter the neural network, well, you can imagine that we have to format them in a special structure, and this structure is of course a torch structure. So the first thing that will happen is that we will convert these images into a NumPy array, then we will convert the NumPy array into a torch tensor, and then finally we will put the torch tensor inside a torch variable that will contain both the tensor and a gradient. That's for our dynamic graphs, to compute very efficiently the gradients later for stochastic gradient descent. So that's our first step, and then once we get the right format of our images, well, they will be able to enter the neural network, and then that's where we'll do the whole propagation of the signals. So let's do this first step, converting the image into the right format. So our images are so far input. So now we're going to create a new variable which I'm calling input. So that's the real input of the neural network. And this input, what is it going to be? Well, first we need to take our input, that is our original images. Then, as we said, we want to convert these images into NumPy arrays. So to do this, we can simply take NumPy, which has a shortcut np, then the function array. So we put input in the parentheses of the function array. There we go, now it is converted into some NumPy arrays. But then, since the cells of the NumPy arrays will contain the pixels, it is actually safer to specify the type float. It's better to make sure we have some float right now, and to make sure of it, we can use np.float32 here. All right, so now we still have a NumPy arrays, but with the type float. All right, and that's also for another reason. It's that tensors are by definition arrays of a single type, and so we choose this single type to be a float, float32. All right, so now that we have our NumPy arrays, the next step is to convert that into a torch tensor. And to do this, we can use, for example, torch dot and then the from underscore NumPy function. So that will convert that into a torch tensor. There we go. And now the last step is to put these torch tensors into a torch variable containing both the tensor and the gradient. And you know how to do it. Of course, we take our variable class, because actually everything that is inside this variable is actually the input of the variable class. But I wanted to show that to you this way because, you know, we start with our input images, then we convert them into NumPy arrays, then to torch tensors, and then to variable. And now we're good. They are allowed to enter the neural network, that is first the eyes of the AI, and then the fully connected layers to lead to the predictions. So speaking of the eyes of the AIs, that's exactly what we're going to do now. We're going to propagate these allowed images now into the eyes of the AIs, that is through the 3 convolutional layers. And to do this, you're going to see now how it's so simple. That's because we already have our brain and our body from the init function. We simply need to take our brain, so self.brain, and apply this brain to the input images. And that will propagate, thanks to the forward function here from the brain, that will propagate the signals inside the brain. And since the forward function of the brain returns the output signals, that is the neurons of the output layer containing the Q values, well, this self.brain input here will return this output signal. And therefore, we're going to put here what it returns into a variable, and we're going to call it, very simply, output. And this output is the output signal of the brain. And now that we have the output signal of the brain, well, we have to propagate this output signal to the body. And to do this, we're going to use the second forward function from the body. And to do this, we simply need to take our body and apply it to, of course, the output. Because the forward function of the body takes as input the output signals of the brain, so that's exactly what the output is right now, and returns the actions. And therefore, since it returns the actions, well, here we're going to add actions equals self.bodyOutput. All right, so now you can see that very simply we propagated the signals inside the brain and then from the brain to the body. First, by using the forward function from the brain, which takes as input the input images and then propagate them into the brain to return the Q values. And then we propagate this output signal into the body with the forward function of our body to get the action to play. And so now the only remaining thing that we have to do, and that's the very last line of code of this part 1, building the AI, well, we have to return the action to play, and that is actions. However, right now the actions have the torch format, and we need to convert them back into NumPy arrays. And to do this, we're going to take the data structure of these actions and then add here the NumPy function. And there we go. Now we have the actions returned in the right format. So congratulations, we are now done with this first part 1. We built the AI in 3 steps. First, we made the brain. Second, we made the body. And third, we assembled the brain and the body. And we propagated the whole signal from the eyes to the moment we play the action. So that's the first step done. That was a huge step. But now, as you understood, we built an AI, but it is still stupid. We need to train it to be intelligent. So we need to train it to do what we want it to do. And to do this, we're going to use the rewards of the Doom environment, because it's learning from the rewards by being reinforced when it gets a good reward and by being punished or weakened when it's getting a bad reward. So that's where the Q-Learning will come into play. And so that's exactly what we'll do in this part 2. training the AI with Deep Convolutional Q-Learning. I can't wait to start, and until then, enjoy AI! Hello and welcome to part 2, training the AI with Deep Convolutional Q-Learning. That's right, now that we built the AI with the architecture of the neural network, the body, the way the actions are played and everything, it's time to train this AI with Deep Convolutional Q-Learning. So that's from now that we will implement, experience replay, working with the Q values, working with the rewards, and there's even going to be a bonus which will improve a lot the training process, and that is called Eligibility Trace. Eligibility Trace is a powerful technique which consists of accumulating the reward over several steps, and the Q values are learned on this accumulation of rewards, as opposed to before, where the Q values were learned after each transition, therefore after getting each reward. This time we will be learning the Q values after getting several rewards instead of just one reward. So instead of having one transition after the other and updating the Q value each time, well, the Q values are going to be updated every n steps, because eligibility trace is rather called n steps eligibility trace, and n is this number after which the Q values are going to be updated. And in our model here we're going to have n equals 10, so that means that will be a 10 steps eligibility trace, and therefore we will update and learn the Q values every 10 steps after accumulating the rewards on these 10 steps. So that's a bonus that will make our model even more powerful, and you will see that in the end we will get outstanding results. I was really amazed when I saw the final results. I used to work on models that took a lot of time to execute. The AI took a lot of time to train, but you will see that with this one, plus the neural network that we made, that is our brain and our body here with Softmax, we will get a very powerful model, and therefore a very powerful AI, because you will see that it will ridiculize Doom. You'll understand what I'm talking about. So, as you can see in this part 2, we are starting by getting the Doom environment, and I actually prepared the lines of code for you. We are just using the image preprocessing external file from our working directory folder. So basically the order is rather to first take this line of code, gym.make ppacket doom corridor v0. So doom corridor v0 is the name of the environment of the game we're playing. So first we import the environment with this gym.make. That's what you can find on the OpenAI gym tutorials. But then we use this preprocess image class, which is a class from image preprocessing, to preprocess the images that will come into the neural network. And we preprocess them so that they have a square format with the dimensions 80 by 80. And that, remember, is because in our neural network, well, we set our input images to have the dimensions 1 by 80 by 80. Remember, 1 is the number of channels, and so 1 means that we're working with black and white images. So that's the grayscale here. And 80 by 80 means that the dimensions of our input images will be 80 by 80. And that is what we set in the neural network, but of course then we need to specify this when inputting the images, which is exactly what we do here with this preprocess image class. And then after we import the environment with the right format of the input images, well, we import the whole game with the videos with this line of code. And remember, the cool thing about this is that in the end we'll see the videos of our AI playing Doom, so we will see how it will kill the monsters, try to reach the vest and everything. So that will be super exciting, and remember that these videos will go into this videos folder. Alright, and last line here, but I want to show it to you because that's important. That's now more related to the AI that we're building. Well, remember that our neural network takes as input number actions. That's because, we want to make an AI that we can test easily on several environments, on several Doom environments. And since the different Doom environments have different number of actions, well, we specified this number actions variable as the input of the CNN, the brain. And therefore, now what we're going to do is get this number actions variable using the Doom environment that we just imported and created into this variable. And later, this number actions variable that we're about to create will be the input of the brain. So let's do this. I'm introducing this real now variable number actions. So number actions equals, now we're going to take our Doom environment, that is the variable that we created. So Doom environment, then we add here dot, And then, well, here we go. We take the first here, action space. That's the set of your actions. I encourage you to have a look at the OpenAI tutorials to see how it works, to understand how the OpenAI gym environments work. But basically, this is the set of actions. And from this set of actions, we can access the number of actions in the environment. And to do this, we add a dot here and n. N is the number of actions. And therefore, doom env.actionspace.n will return 7. It will return 7 because there are 7 actions. I know that we can see 6 actions in the doom environment on the OpenAI gym page, but I think we can also run. And so, we can move forward, move left, move right, turn left, turn right, and shoot. And besides, we can run. So that makes 7 actions. All right, and that's it for getting the doom environment. We have the doom environment, we have the number of actions. So we have so far everything that we need for our brain. We will then just create an object, a brain object, which we'll call CNN in minimal letters. And since the init function takes number of actions as argument, well, we will input the number of actions in the CNN object that we will create. And then, of course, we will create the body and eventually the AI. And that's why the next section, I'm going to call it building an AI, because now we can build as many AIs as we want. That's the awesome thing about object-oriented programming. We can build any AIs as we want. And so we're going to build our AI that has this sophisticated brain. And that's exactly what we'll do in the next tutorial. Until then, enjoy AI. Hello and welcome to this tutorial. Alright, so now time to build our very first AI. Because right now we've only made the manual of instructions with the AI class, but we haven't created any object yet, and so we haven't a real actual AI yet. But we're about to get it right now because we're about to create one object of this AI class. And this object will be nothing else than an AI which will have a brain and a body. Alright, so let's do this. It's actually very simple to do it now that we have defined everything with the classes. So basically what we need to do is first create a brain, because as you can see, when we create an AI, we need to input a brain, but we also input a body, so we need to create a body as well. And then once we created a brain object and a body object, well, we will be able to create the AI. But no worries, we will build the brain and the body in a flashlight, and actually let's do it right now. Let's start with the brain. We're going to call the brain CNN, because the brain is a convolutional neural network, and it will be an object of the CNN class, so it makes sense to call it CNN. So CNN equals, and then we take our CNN class this time, and we input, in parentheses, according to you, well, at this point right now when we create an object of a class, what we have to input is very simply the argument of the init function. And that's number actions, and thanks to what we did previously, when getting the doom environment, well, we already have this number actions, and therefore we simply need to input number actions here into the CNN class. Perfect. So now we have the brain. Now let's make the body. We're going to create an object of the softmax body class, and we're going to call this object softmax body. That will be the body of our AI, and this object is an object of the softmax body class, to which we have to input the only argument of the init function of the softmax body class, which is the temperature T, and therefore here we input T, but we have to specify a value because so far T is just an argument. So T equals, and we're going to start with 1. That's a small temperature, but this might work very well, and actually I already know this will work very well. So, but you can try with other temperatures. You know how it works now. Your actions will be more sure of themselves. That is, the action with the highest Q value will have a higher probability to be selected as opposed to the other actions which will have lower probabilities to be selected, and therefore there will be less explored. But anyway, we can start with 1. This will get us a good body. Alright, so now we have a brain, we have a body, so I guess it's time to make the final AI, eventually. So now you're going to see how things are going to become so simple. It's when the intuition reaches its peak. To make an AI, we simply need to create an object that we call, of course, AI from our AI class. And since an AI is composed of a brain and a body, we input the brain, which is our convolutional neural network, but the object, and a body, which is nothing else than the softmax body object from the softmax body class. And see, we built an AI in a flashlight by just inputting a brain and the body, and now we have an AI ready to be trained. So now it's time to launch the whole Deep Convolutional Q-Learning process with experience replay, that bonus of eligibility trace on 10 steps, and eventually, once we have all this, we will train the AI to make it smart. So, can't wait to do this. The next section is going to be about setting up experience replay. So we're not going to implement it all over again like for the self-driving car, because the good news is that we already have it implemented. So that will be fast. We will just create an object of the replay memory class that is in this experience replay file. So that will help us a lot, and therefore we will move on quickly to what's new and most important, that is the training. So let's attack this in the next tutorials, and until then, enjoy AI. Hello and welcome to this tutorial. Alright, so now we have our AI, it is ready to be trained, and the first step of the training is to set up experience replay. So we're slowly getting there, the training, and the good news is that we have an implemented version of experience replay, besides that is adapted to eligibility trace, which I remind is a technique that instead of learning the Q values every transition, learns it every 10 transitions. So basically that's exactly the same as before, but instead of having a single target, a single reward for each step, we're going to have a cumulative target on 10 steps and a cumulative reward on 10 steps, and we will learn on the 10 steps each time. So we are learning on 10 transitions, 10 steps, instead of one like before. And with this, our AI will work wonders. And that will make some wonders for the training process. You know, the training will take much less time, thanks to this technique, but we have to specify in experience replay that we are learning every 10 steps. So that's why this experience replay is not a classic implementation of experience replay like the one for the self-driving car. It is an experience replay implementation taking into account this 10 steps learning. And therefore you will find in this experience replay file two classes. One class that makes your AI progress during 10 steps so that it can sum the rewards observed on these 10 steps. That's the first class. And we need this class because we need to include these 10 steps in the replay memory class, which is the class we implement for experience replay. And that's how we make sure that the memory also takes into account the fact that we're learning on 10 steps. So that's why you will find two classes in this implementation of experience replay, but that's only to take into account that we're learning on 10 steps, and that must be taken into account also in the memory. So speaking of our memory, let's create it. We're going to call our memory, and so memory is going to be an object of the replay memory class. And the replay memory class is a class of this experience replay py file. And so I'm taking first this file, experience replay, then dot, and that's where I take the replay memory class. Perfect. And now as you can see, we have to input two arguments. The first argument is n steps, which corresponds exactly to the number of steps on which we're going to learn the Q values. So you know the number of steps on which we accumulate the target and the reward. So we're going to have a cumulative target and a cumulative reward. And then the second argument is the capacity, that is the size of the memory. So for example, here we can see 10,000. So if the capacity is equal to 10,000, that means that the memory will have a size of 10,000, and therefore that means that we will get a memory of the 10,000 last steps performed by the AI. But again, we're not going to learn every transition, we're going to learn every 10 steps among these last 10,000 steps of the memory, and that's exactly this new feature that we introduce here compared to before. Before we only had this replay memory trick, and here we have this replay memory trick plus this trick of learning every 10 steps. And we're going to learn every 10 steps, and we're going to do it in the memory composed of the last 10,000 steps. And this, that is experience replay combined to an eligibility trace with 10 steps, will considerably improve the training performance. So let's input these two arguments. The first one is n steps, and that will be equal to, well, for now, let's say n steps. We will specify what n step is right after that. It will actually be an object of the other class of this experience replay file, which is the n step progress class, and that allows to make the AI progress during 10 steps. And remember, during the 10 steps, we will sum the rewards on the 10 steps to get the cumulative rewards over 10 steps. And that is exactly eligibility trace. So now what we have to do is create this end steps here. And we create it with the second class that we have in this experience replay file, which is end step progress. So now we're going to create end steps like this, and this will be an object of the end step progress class that we take again from our experience replay file. There we go. So that's the end step progress class. And now we have to input 3 arguments. As you can see, we have to input the environment, which is the Doom environment here that we imported. Then the second argument is our AI, and this will be, of course, the AI that we built right here in the previous section. And the last argument is end step, and that's where we'll specify that we want 10 steps, to learn every 10 steps, that is every 10 transitions. So let's input these arguments. The first one is the environment, and that's Doom env. All right. Then the second one is our AI, and that we called it AI. That's the one here. So this is just the name of the argument of the end step progress class, and this AI here is our AI, the one that we built. And then the last argument is end step, and that is equal to 10. All right. So right now we're just taking into account in the memory that there is a learning on 10 steps, and this learning on 10 steps is called Eligibility Trace. So we're really working on the advanced stuff here, but remember that's because we're trying to beat Doom. That's nothing like making a piece of cake, so we need these advanced techniques to make it work. So now we're almost ready before moving on to the next step, which will be actually about implementing Eligibility Trace. The only thing that we have to include is the capacity, of course, and that is, let's say, 10,000. The memory will have a size of 10,000, meaning that the memory will contain the last 10,000 steps performed by the AI. And that will allow us to generate some mini batches, as you remember, with the sample function. The memory contains 10,000 transitions, but to train the AI, we're going to sample some mini batches of 10 transitions, not one compared to before, 10 transitions this time, and we will sample these mini batches of 10 transitions in the memory composed of the 10,000 last steps. Alright, so now I guess we're ready to move on to the next step, which is about implementing Eligibility Trace. So we're going to have some adventure here. This will not be a simple implementation, so have a good break, and when you're ready, we can attack this. Until then, enjoy AI! Hello and welcome to this tutorial. This special tutorial is going to be super exciting because we are getting closer to the A3C algorithm. You're going to see that what we're about to implement, and that is called Eligibility Trace, or SARSA, is actually an algorithm of the asynchronous actor-critics agents algorithms, but we cannot consider it an A3C because we're still going to have one agent. But still, you're going to see that what we're about to implement is actually taken from the following paper, which is this paper, Asynchronous Methods for Deep Reinforcement Learning. And it is in this paper that you will find the A3C algorithms that we will implement as the final bonus of this course. But as I said, we're getting closer to it because the model that we will implement right now is actually this one, the asynchronous end-step Q-Learning. That's the one. So that's almost the A3C, which is the one after that, but with one agent. And the powerful thing about this is this end-step Q-Learning. We're going to learn the cumulative rewards and learn the cumulative target on end steps instead of one step like previously, and that's what will make the training much more performant and therefore our AI much more powerful. So we actually have the pseudocode for this algorithm. It's this algorithm S2 right here. So let's click on it, and there we go. That's the algorithm we're about to implement, but remember, with only one agent. The difference is that here they take an action AT according to the epsilon greedy policy based on the Q values for the current state and the action played. But in our case, we didn't implement an epsilon greedy policy. We implemented a softmax, but the rest is the same. As you can see, we're going to compute the cumulative reward on n steps, actually 10 steps. Remember that n steps is equal to 10. And so we will implement this line of code in our algorithm that we're about to implement right now. We're going to get this, and mostly we're going to implement this as well. You'll see that we will get the maximum of the Q values for the current state and the current action. And this theta here is just the target parameter. So let's do this. Let's attack this algorithm. This one is called the asynchronous n-step Q-Learning, but we don't have the right to say asynchronous as far as we're concerned because we only have one agent. But therefore we can call it n-step Q-Learning, Eligibility Trace, or even SARSA. Alright, so let's do this. It's gonna be pretty fun. We can basically follow the pseudocode here, and that's what we're gonna do. And so, as you can see, a parameter that we'll need is a gamma, the gamma parameter, that is the decay parameter, and therefore we will start by introducing a variable for this gamma parameter and choosing a value. So let's do this. We actually don't need a class to implement this. We can simply implement this with a function because we don't really need to create objects for this eligibility trace model. A function will be enough because basically what we want to do is to return the inputs and the targets so that later, when training the AI, we are ready to minimize the distance between the predictions and the target. And to get the predictions, we need the inputs because we're going to apply our brain on the input to get the output signals. That will be our predictions. And then once we have our predictions and our targets, we will be ready to train the AI by trying to minimize the square distance between the predictions and the targets. So that's the whole point of doing this right now. We are implementing this function to be able to return these inputs and these targets so that we can be ready for the training to minimize the square distance predictions minus targets. Alright, so let's do this. As we said, we want to implement a function, so we start with def. This function, we're going to call it eligibility underscore trace. You can also call it SARSA, you can also call it n-step Q-Learning, whatever you want, but let's call it eligibility trace. And this function is going to take one argument, which is going to be a batch. And why a batch? It's because we're going to get some inputs and some targets because we're going to train the AI on batches. And so the inputs and the targets will go inside some batches. And therefore the input argument here is this batch that will contain several inputs and then several targets that we will compute. So there we go, that's the only argument we need. Now let's go inside the function and let's define what we needed to do. So as we saw in the pseudocode of the paper, we need a gamma parameter. So as we said, we start by introducing this gamma parameter. So gamma equals, and we can already decide for a value, and we're going to choose 0.99. That's a classic good value for the gamma, and no worries, I checked that this is a good value for our AI. Alright then, next step. Next step is to prepare our inputs and our targets, because that's exactly what we want to return. We want to return the inputs and the targets to prepare the training. And so we can already initialize them with an empty list, because of course in these inputs inside the batch, we're going to have several inputs all into a list, and that's why I'm initializing the inputs as a list as well as the targets. There we go. So we initialized our inputs and our targets, and in the end, this eligibility trace function will return exactly these inputs and these targets, but of course filled in. We will have several inputs and the associated several targets in what will be returned by the function. Alright, next step. Next step is to start a for loop, and that's exactly because we're following the pseudocode of the paper. This pseudocode, and as you can see, there is this repeat code section, and repeat is exactly a for loop in pseudocode. We're going to compute the cumulative reward right here, accumulated over the 10 steps. And how is it computed? Well, in each step that is not the last step, we're going to get the maximum of the Q values of the current state we're in during this n steps run. And if we reach the last state of the 10 steps, well, this will be equal to 0. That is, we don't want to update it anymore. And then we have this for loop, which is going to be another for loop. They don't say repeat here, but that's the same. It's going to be a second for loop in our algorithm. Well, we will update the reward this way by multiplying it by the decay parameter gamma and adding the reward. So let's do this. Let's go back to Python and let's start our for loop. So for, and what is going to be the iterative variable? Well, that's going to be our 10-step series, our series of 10 transitions. So we're going to call this variable series. So that represents a series of 10 transitions, like a sequence of 10 transitions. So for series, in, and then what do you think? Well, our series will belong to our batch. That is the batches on which we will train the AI. And so for series in batch, that is for all the series of 10 transitions in our input batch, well, what are we going to do? Well, to get the cumulative reward, you will see in the pseudocode that we need the state of the first transition of the series and also the state of the last transition of the series. So what we have to do right now is get these input states. And so we're going to put these two input states into a variable that we're going to call, and we will get these two input states, the first one of the series and the last one, that we're going to put into a NumPy array. But no worries, we will not stay with this NumPy array. We will of course convert that into a torch variable. But the first step is to put these two input states, the first one and the last one, into a NumPy array. And so right here, in this NumPy array, we add the first input, which is the input state of the first transition of the series, and that is series. And then to take the first transition, we take the index 0 of the series. That's the first transition. And then we can access it by taking its attribute, which is state. And that's because in our experience replay file, we defined a special structure for each of the transition. And you know this structure. Each transition is composed of a state, an action, a reward, but then a last element, which is done. So this special structure that we're allowed to use right now comes from the way we defined a transition in experience replay. Alright, so with this we get the input state of the first transition, and now let's get also the input state of the last transition of the series. And to do this, that's the same, we can just copy this and paste it and replace the 0 here by the last index of the series, which we can access with this trick, -1. Series -1.state will get the input state of the last transition of the series. Alright, then we need to put these two elements inside some square brackets, because that's what is expected by the NumPy array function. And then an important thing to do, since we are going to convert that into a torch tensor in a torch variable, well, remember, a torch tensor is by definition a special array containing one single type, and so we need to force having one single type, and as usual we're going to choose the float type. And so I'm adding this parameter here, dtype equals np.float32, we can take this one, and now we can convert that into a torch tensor in a torch variable. So let's do this. To do this, well, first let's convert that into a torch tensor. And remember, we can use torch.from NumPy. There we go. And we put all the array of the two input states inside this torch tensor with the torch from NumPy function. Perfect. So that will convert this arrays of the two input states into a torch tensor. And now we put this torch tensor into a torch variable using the variable class. So input will be an object of the variable class, and in fact, as you understood, this variable class takes all this as an argument, and that creates the object. Alright, so now we should be good. We have our two inputs that we need, that is the input state of the first transition and the input state of the last transition. And now that we have the input, well, what can we get? We can get the output signal of the brain of the AI, that is the prediction. But we're going to call it output. That's the output signal. And to get the output, well, now that's very easy because we already have a brain created, which is our convolutional neural network. And so we can simply take our brain, CNN, applied to the input, which will return the prediction, that is the output. As simple as that. And now we are already ready to move on to the next step. And the next step is to start to compute this cumulative reward. So now we're going to do exactly the same as our S2 algorithm, the SARSA, or should we call it n-steps Q-Learning. We're going to introduce the cumul reward variable, which will be the cumulative reward. And let's go back to the paper. As you can see right now, what we have to do to get this cumulative reward, which is R here, well, at each step of the 10 steps run, we need to update it by adding a 0 to this cumulative reward if we reached the last state of the series, or the maximum of the Q values if we haven't reached the last state of the series. That is, for all the steps except the last step. So let's simply implement this. So let's go back to Python. So this cumulative reward, as we just saw, is going to be equal to 0.0 if we reached the last state, and we can write this condition this way. If series of index -1, that is the last transition of the series, then we add dot done, because done actually is an attribute of, this transition structure that we defined in experience replay, our experience replay file. And this done comes from actually the OpenAI structures, because if we go to the OpenAI gym website, which is actually right here, I prepared it. So that's the Doom corridor v0. And if we go to documentation, and then so that's the tutorial. I really encourage you to have a look at it. You can run an environment, but mostly you can see that our observations, that is our transitions, are defined by an observation, a reward, and this done here. And this done means exactly that a transition or a step is over. And so we're going to use this done here for our if condition. Therefore, if series -1.done means if the last transition of the series is over, is completed. And so this cumulative reward is going to be equal to 0 if the last transition of the series is done, and else, if we haven't reached the last transition, well, cumulative reward is going to be updated with, as we said, the maximum of the Q values. And since this output here is the output of the brain, that is the predictions of the neural network, and as you know, the predictions of the neural network are the predicted Q values, well, this output contains the Q values, and since we need to take the max of the Q values, well, we need to add first this index, because this structure contains the Q values in the index 1, and then we need to add data to access the data of this output structure. It has this special structure of a torch variable. So with this, we get our Q values, and now we want to take the maximum of our Q values, and so simply we add dot max. And now we get exactly what we want as in the paper. This maximum of the Q values for the non-terminal state ST. Perfect. And so now what we're going to do is make this second for loop. That is, for the 10 steps of the series, we are going to update the cumulative reward this way by multiplying first by gamma, the decay parameter, which we already have, and then adding the reward. So let's do this. We are actually going to do exactly the same as in the pseudocode. As you can notice, they start from the right, so they're not starting with the first step and going to the last steps. They start with the last step, t-1, up to the first step, t-start. So that's exactly what we're going to do, and that's because we want to get, in the end, the cumulative reward being equal to r equals r0 plus gamma r1 plus gamma squared r2 plus dot 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 plus gamma at the power of 10 r10, where r1, r2, dot 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 r10 are the rewards obtained in each of the n steps of the series. So let's take a quick break before attacking this second for loop, and I'll see you in the next tutorial. Until then, enjoy AI! Hello and welcome to this Python tutorial. So let's do this. Let's make this for loop starting from the right and going to the left. And to do this, we're going to add 4. So this time the iterative variable is going to be our step, because we're going to go from the last step to the first step of the series of transitions. And so 4 step, and now the trick to go from the right to the left is to use for step in reversed. Reversed. And now we just need to input a sequence, and this sequence is going to be, of course, our series. So we input our series, but as you can see in the paper, we go from t-1 to t-start. So we don't go from the last step, that is the terminal state, but the state before that, that is t-1, but to t-start, that is the first step. And so here, to go from not the last state, but the state before, we need to add in brackets colon -1. I'm sure that for those of you who followed the machine learning and the deep learning course, you know this trick. Colon -1 means that you're going up to the element before the last element, but not up to the last element, and therefore we get the sequence we want. That is, we're going to go from the element before the last element up to the first element. And that we do thanks to reversed, to go from the right to the left. Alright, so we are ready to enter the for loop. And so inside this for loop, what are we going to do? Well, we're going to do exactly as in the paper. We're going to update the cumulative reward by multiplying it by gamma and adding the reward obtained in the current step, that is, in the step of the for loop. All right, so let's do this. Going back to Python, and so we want to update our cumulative reward the following way by first multiplying it by gamma. There we go. Here we multiply it by gamma, and then we want to add the reward of the step, which we can access this way with this special structure. Remember that reward is an attribute of the step object. And so here, of course, we add a plus. All right, so cumulative reward equals the reward of the step we're in right now, the loop, plus gamma times the previous cumulative reward before it is updated. Perfect. So now I think we're good. We're following thoroughly the algorithm. And now, time for the next steps. Well, now it's going to become pretty easy. We go back to the first for loop, because this for loop is just to compute the cumulative rewards, going from the right to the left by updating this way, following the algorithm. And now, as you remember, the goal of doing all this is to get our inputs ready and our targets ready so that we can minimize the square difference between the two for the training. And so right now, the only thing that we have to do left is get these inputs and targets ready. So let's do this. First, what we need to do is add the first state of the series in our inputs list. So far, this input state is in this input variable, but that was just to compute the output. So we're going to get this input state of the first step separately, because that's exactly what we need to append in our inputs list. So let's get this separately. Therefore, we're going to call it state. And so exactly the same as here, we can get it this way by taking the first index of the series, which contains the first transition, and then adding .state to get the state of this first transition. So that's the state we need. Then same, we're going to get separately the target associated to this input state of the first transition. And so I'm introducing a new variable here, target, which will be equal to the Q value of the first step. And since the Q value is returned by the neural network, it is contained in output. And since output is the output associated to this input, which contains the first element of the transition, well, we can get this Q value of the first state by just taking output here and taking the index 0. And then we add .data. That will simply get us the Q value of the input state of the first transition, and that is exactly the target Q value. So that's why we're taking it. Then we are going to update this target variable, but only for the action that was selected in the first step of the series. And to access this first step of the series, well, we need to take first series 0, because this is exactly the first step of the series 0. And to access the action corresponding to this first step of the series, well, we need to add here .action. Again, that is this attribute structure that we're using. Action is an attribute of the first step of the series, that is the first transition of the series, because each transition of the series has the following structure: state, action, reward, and done. So action here, this attribute action here, means that we're simply getting the action of this first state. And so the target for that specific action of the first step is exactly what needs to be updated by the cumulative reward. So basically here we're just going to write that the target associated to the action that was played in the first step of the series is this cumulative reward that we just computed. All right, and now we're finally ready to update our input by appending this first input state here and this first target here for the first step. We only need to update the first step of the series because we train the AI on 10 steps, and therefore the input is the first step of the 10 steps, and also we get the target in this first step. But then we don't need to get any inputs or any targets in the following steps of the 10 steps, because basically the learning happens 10 steps afterwards. So that's why right now we're only getting the state and the target of the first step of the series. So it's important to understand that, and therefore if we understand that, then now we understand that we have to input them in our list of inputs and our list of targets. So let's do this. First, let's append the states to our input. So we take our inputs list and we use the append function to add the state, which remember is the input state of the first step of the series. And then we are going to append the target of the first step to our list of targets. And to do this, we take our list of targets, and same, we use the append function to append this first target. There we go. Almost done. And now we need to return the last things, which are, of course, what we need. That's what we said at the beginning of this tutorial. The input and the targets that are now updated. So we're going to add here return. Then we're going to get our inputs first. But then that's the same. We need to convert them into a NumPy array first. Then do a type conversion to make sure we have a single type with dtype equals np.float32, the same. And then we convert this into a torch tensor because of course we're working with PyTorch, so that's totally compulsory. And so I'm using the torch from NumPy function again, and that gives us our inputs. Perfect, and now let's do the same for the targets. Now we're going to use this trick, which is quicker. We're going to stack the targets together, and to do this we need to take first our torch library because we're going to use the stack function by torch to stack the targets. Alright, and so this line of code basically returns the inputs and the targets that were just updated through this eligibility trace SARSA algorithm, or we can call it n-step Q-Learning. And so now, congratulations, we are ready to do the final training, because basically the training consists of minimizing the squared differences between the predictions of our inputs and the targets. So let's get our AI smart. It will become smart in the next tutorial, and so until then, enjoy AI. Hello and welcome to this Python tutorial. So now that we are ready to train the network to minimize the squared distance between the outputs and the target, thanks to what we did with Eligibility Trace in the previous section, well, basically we're ready to start the whole training by, getting our inputs, our targets, our predictions, then computing the loss error between the predictions and the target, and then doing the backward propagation with stochastic gradient descent to update the weights. So we're ready to do all this, but since we want to compute the moving average on 100 steps, to keep track of the average during the training, well, just before we do this whole training, we are going to make a class right now that will get this moving average on 100 steps. So no worries, we will do it quickly. We will make a class with 3 functions, but we will do all this in this single tutorial. So we will do it quickly. We already did it, and besides we want to focus on the training right now because that's the most important. So let's make this class right now in this single tutorial. Alright, so we are going to introduce a new class, which we're going to call MA for moving average. And then here we go with our first function. So that's of course the init function, that never changes. Init, and this init function is going to take 2 arguments. The first one is self for the moving average future object, and size, which will correspond to the size of the list of the rewards of which we're going to compute the average. So this is going to be 100. Alright, so we have our arguments for the init function. And now let's go inside the function. Now you know what to do. We have to initialize the variables specific to the object. And these are, well, the first one is going to be a list of rewards. So that's going to be the list containing the 100 rewards of which we're going to compute the average. So here right now we're just simply initializing this list with this empty list here. So list of rewards, and then the second variable of our future object is going to be, of course, the size. And the size is going to be equal to the argument we will input when creating the future moving average objects. So size here, and already we are ready to move on to the next function, which is going to be the add function, and that will add the cumulative rewards. Be careful, it's not the simple reward, it's the cumulative reward, and that's because we are doing eligibility trace and therefore learning every 10 steps and therefore learning with cumulative reward and not a simple reward. So this add function that we're about to make will add the cumulative reward to that list of rewards. So def, we're going to call it add, of course, and this add function is going to take 2 arguments. The first one is self, because we're going to use this list of rewards here, because simply we're going to append the cumulative rewards to this list of rewards. So we need this self to be able to get this. So self, and the second one is going to be the reward, which will represent the cumulative reward. All right, so that's our two arguments of the add function. So now let's go inside the function and let's define what it has to do. Okay, so very simply, the first thing it has to do is whenever we get a cumulative reward, a new one, when we progress on 10 new steps, well, what we have to do is add this cumulative reward to the list. And that's exactly what we're going to do. We're going to write a line of code that will add this new cumulative reward that we're getting after progressing on 10 steps to this list of rewards here. And to do this, we have to separate two conditions, because since we will be working with batches, well, the rewards will be in some lists, but in some other cases, the rewards can also be as a single element. And the syntax to add an element to a list, which is the list of rewards here, is not the same whether you're adding a list or a single element. So we just have to make this condition that will separate these two cases. And let's start with the first case, which is the case when what we're adding to this list of rewards is a list. And to do this, we're going to add is instance, and in parentheses, we input two arguments. The first one is our rewards that we're adding, so rewards, and the second one is list. And so if is instance rewards list means if the rewards are into a list. And so if the rewards are into a list, what we do is very simply self dot, we take our list of rewards and we are going to add this list. Because since this is a list, what we can do is use a simple addition operation, because we can sum two lists together. The rewards here is a list because this will be equal to true. If we're in this case. And so we can simply sum this list to our list of rewards. And therefore, we can simply add here list of rewards plus equals rewards. And by doing this, we're just extending the list by summing these two lists together. All right, and then second condition, so we can simply add else. So that's if the rewards is not a list, and therefore if it's a single element. And so else, what happens in that case? Well, that's the same. We want to add the reward to our list of rewards, but we cannot use this syntax because rewards will no longer be a list. It will be a single element. And so what we need to use is another syntax, which is the append function. When you want to add a single element to a list, you cannot sum the two, you have to use the append function. And so this is exactly what we're going to do now. We are going to take our list of rewards of the object and paste that here and then add dot append, there we go, first one. And of course in parentheses we input the element we want to append. And this is of course reward, but rewards in that case will not be a list, it will be a single element, like a single cumulative reward, not into a list. All right, and then we want to do this, but now we have to add something more. It's what does happen when this list of rewards gets more than 100 elements. Well, in that case, what we have to do is delete the first element of this list of rewards to make sure that this list of rewards always contains no more than 100 elements. So exactly like what we did for the self-driving car when making the score window. And so to make sure of this, we're going to add a while condition specifying that whenever the length of our list of rewards, that is the number of elements in our list of rewards, whenever this number is larger than self.size, that is the size that we set here and which later will be equal to 100 when we create the object, well, as soon as the number of elements of this list of rewards is larger than 100, well, what we want to do is delete the first element of our list of rewards, which we can get by taking the index 0, that is the first index of our list of rewards. This is the first element of our list of rewards, and we want to delete it whenever our list of rewards contains more than 100 elements. So that with this condition here, we make sure that our list of rewards never contains more than 100 elements. And therefore, now what we can do is make a new function to compute the average of our list of rewards, which will contain on the run 100 elements. And therefore we will compute the moving average on 100 steps each time. So let's make this new function. It's going to be very easy because there is the mean function in Python, which is a function from NumPy to compute the average of a list. And so let's introduce our last function here, which we're going to call average. And this function is going to take one argument, which is going to be self, because we're going to use, of course, still our list of rewards, which is a variable of our object. So self and colon. And now let's compute the average. And so directly we will return the average because we can get it with the mean function, to which, of course, we are applying, well, what we want to compute the mean of, that is our list of rewards. I think I still copied it. Yes, there we go. So we simply return the mean of our list of rewards. And the mean, as I said, is a function by NumPy. So here I'm adding the shortcut np.mean self list of rewards. And there we go, we have our average on 100 steps. Perfect, so we made that class very efficiently. Now we get the instructions on how to obtain a moving average on 100 steps. And since we're going to use one moving average object when doing the training, well, let's already create this moving average object. And so we're going to call it MA. And simply MA is going to be an object of the MA class. And as we said, we want the size to be 100 because we want to compute the moving average on 100 steps. So perfect, there we go. We're now ready to train our AI to finally be intelligent. It's about time. It is from this point that our AI will become smart. So I can't wait to train it. It's going to be quite easy because this is something we already did, but this is going to be fun. And besides, after that, it will be time to have even more fun because basically our AI will be fully ready, that is built and also intelligent. And therefore we will execute the code and then our AI will play Doom and eventually we will watch the videos of our AI playing Doom and we will see if it manages to reach the vest. So I can't wait. Let's do that. And until then, enjoy AI. Hello and welcome to the super exciting part of our AI creation, the part where we make it smart. So that's exactly what happens when training the AI. We will train its intelligence to reach the goal we want it to accomplish, that is, reaching the vest without getting killed. And to do this, we're going to basically train the neural network to output the right predictions, and then everything is already ready because these output signals from the brain already have the right transmission to the body to play the final actions. So basically, now what we're about to do is something we already did before. We are just going to take some random batches from the memory, get our inputs from these samples, get the outputs, get the targets, get the predictions, compute the loss error between the predictions and the targets, and then perform backward propagation with stochastic gradient descent to update the weights according to how much they contributed to this loss error. So let's do all this. You're going to see how it's going to be so easy because we already have all the tools to implement this. Not only we have the PyTorch tools like the optimizer and the loss functions, but also we have all the classes that we made before, like our brain, of course, which we're going to use to get the predictions, then our experience replay implementation, eligibility trace, and all these tools combined to the PyTorch tools will make the training super performant. And therefore, eventually, we will get a super powerful AI. So let's make this training happen. Let's make our AI smart. And the first thing we're going to do now is get the loss function that we'll use during the training when computing the error and an optimizer. That's the first thing we'll do. So let's create a variable for the loss function. We're going to call it loss. And this will be equal to the MSE loss function from the NN module. nn.mseloss. That's the loss function we'll use because basically our predictions are Q values. We're predicting the Q values of the different actions. And therefore, since these are real numbers, well, we're kind of doing some neural network for regression. And therefore, the loss function is the mean squared error. That's the loss function we use in general for regression. All right, so now that we have our loss function, let's get our optimizer. So optimizer here, that's the variable we create for it. Optimizer, and we're going to take, as usual, as for the self-driving car, the Atom Optimizer. That's a very powerful optimizer that will work wonders for the training. So let's get this one, optim.atom, and remember, that's exactly for the self-driving car. We have to input two essential arguments. The first one is the one that will make the connection between the optimizer and the parameters of our neural network. That is the weights of the neurons of our brain. And to do this, we take our brain, which we called CNN. That's the object we created for our brain. And so CNN dot, remember, parameters. There we go. And some parentheses. So that makes the connection between the optimizer and the weights of the neurons in the brain of our AI. And then the second argument is a learning rate. And that's given by LR. And so here we have to take a small learning rate because we don't want to converge too fast and we want to have some exploration. And therefore a good learning rate that we can take here is a small one that is 0.001. That is 0.1%. I think that's the same we used for the self-driving car. Alright, so now we have a loss function, an optimizer. So we are almost ready to start the for loop. Well, actually, we will start the for loop right now. But just before we do it, we're going to decide the size of the number of epochs we will be training the AI. And therefore, I'm creating a new variable here, which will correspond to this number of epochs. And let's set it equal to 100. That will be way enough to train the AI. And I even bet that the AI will manage to reach the vest way before 100, like 20 or 30. Let's see, but for now, let's take 100. And if we need it, we will increase it. But I don't think that will be necessary. Okay, so now that we have our number of epochs, we can start to make the for loop. You know, this main for loop of the training when we train over the epochs. So for, then the iterative variable is going to be epoch. That's what we choose. For epoch in, now of course we're going to use the range function to say that we want to go from the first epoch, 1, to number of epochs, plus 1. Because remember, the upper bound of a range is not included. And therefore, if we want to go up to 100, well, we have to specify nb epochs plus 1 to go up to 100. Alright, so colon, and now let's get into the loop. Alright, so the first thing we're going to do is to do 200 runs of 10 steps. So each epoch will be 200 runs, one after the other, of 10 steps. And to do this, we have this runSteps function from our experience replay class. And therefore, to use this function, which is actually a method because we will get it from our memory object, which is an object from the replay memory class, to generate these 200 runs of 10 steps, well, we have to take our memory object that I remind we created right here. Memory is an object of the replay memory class with n steps, that is 10 steps, and a capacity of 10,000. We created this object, and from this object, we take, well, this runSteps function. runSteps, and we specify 200 successive runs of 10 steps. So that will just, at each epoch, basically run 200 steps. And now that we have these 200 steps running at each epoch, well, it's time to sample some batches from these runs. And to sample these batches, we have another function from our memory, which is sampleBatch, and that will exactly generate some batches from these 200 runs. But remember, these batches are this time batches of series of transitions, that is series of 10 steps, as opposed to before where the batches were just some batches of single transitions. Here this time, they're going to be batches of 10 steps, 10 transitions. And therefore now it's time to get from our memory these random batches, and to get them we use the simple batch function to which we have to apply the batch size. And for the batch size, well, we can take 32 or even 64 or even 128. Remember, for batch sizes, it's a common practice to use 32. That's what you will see in general in the neural networks architectures when doing some batch learning. But this time it's quite different. We're just sampling some batches of 10 steps. So it's better to take batches with larger sizes. So that's why we can take 64 or 128. So we're going to take 128. And actually, this is going to be inside a for loop. Because we want to take several batches, and we're taking them in what is returned by this sample batch function. So this for loop for batch in memory sample batch 128 means that every 128 steps, well, our memory will give us a batch of size 128, which will contain actually the last 128 steps that were just run. We're just getting some batches of size 128, and the learning is going to happen on these batches. And besides, inside these batches, we will have eligibility trace running, to learn every 10 steps. All right, so now inside this loop, which is still happening in one epoch, but now this time we are in a specific batch. And so now the first thing we're going to do is we're going to get our inputs and our targets separately. And that, as I told you, it's very easy. We can do it with one of the tools we implemented, which is Eligibility Trace. As you can see here, this Eligibility Trace function takes a batch as input, and now we have the batch, and returns as output the inputs and the targets. So right now what we can simply do is create two new variables, which are going to be the inputs and the targets, and do this. Input, comma, targets equals exactly what returns this eligibility trace function applied to a batch. So we will apply this function to the batch of our loop, and so what we'll do is just eligibility trace applied to the batch of our for loop. All right, so that gets us the inputs and the targets. But in PyTorch, there is always something more we have to do. And of course, this is to convert the inputs of the neural network and also the targets into some torch variables. But no worries, there is nothing new. We know how to do it. We can do it this way. We take our inputs, then our targets, and well, they will be equal to variable inputs, that's for the inputs, and variable targets, and that's for the targets. All right, so the inputs of the brain are converted into some torch variables, and the targets also are converted into some torch variables. So now we can get the input enter the neural network. And why do we need to do this? That's because the next step is to get the predictions. We have the inputs, we have the target. Now, of course, we need our predictions, because then what happens is that we will compute the loss between the predictions and the targets. So let's get these predictions. To get them, well, again, this is so simple now. We just need to take our brain, which is CNN, our convolutional neural network, and apply it to our inputs. There we go. The inputs go into the neural network, and the neural network will output the predictions. Perfect. So now we have the predictions, we have the targets, so we can get the loss. And that's the next step. We're going to introduce a new variable, because right now we're going to get the loss error, which is different than the loss function, because we use the loss function to get the loss error. So loss error here, and that we will get it with the loss function applied to our predictions and the targets. There we go. See how everything is smooth now? Everything is logical. We get the input first, the targets, then thanks to the inputs we get the predictions, and then thanks to the predictions and the targets we get the loss error. So very logical and smooth. And now what is the next step? Well, same logical path. Now that we have the loss, we can back propagate this loss error back into the neural network to update the weights. And we do that with stochastic gradient descent. And to perform stochastic gradient descent, we need our optimizer, but we already got it here, our Atom optimizer. But now at this point, remember what we have to do? We have to initialize it. And to initialize it, remember we take our optimizer object, and then we apply the zero grad method. There we go, we don't forget the parentheses. That initializes it. And now next step is to backpropagate the loss error back into the neural network. And to do this, well, we take our loss error and we apply on it the backward method. So that's exactly to apply backward propagation. And then finally, now that the loss error is backpropagated into the neural network, well, we can update the weights with stochastic gradient descent. And to do this, remember, we take our optimizer and then we apply the step method. There we go. The weights are now updated. As I told you, not only we already did it, but now it seems so simple and so natural. So now we're going to do something fun. We're going to print the average reward every epoch. So we can keep track of how the AI is going, how the training is going. We want to see the average reward increasing over the steps, over the epochs. And at first, of course, there is this exploration phase, so the average reward might not increase at the beginning, but then once it reaches the exploitation phase, then we'll see the average reward definitely increase. And it will increase up to a certain level, which is when it reaches the vest as fast as possible. So let's start with a print. We are doing this in one epoch, so we have to go back to the loop here. Print, and then we're going to print, well, first epoch, a colon, then %s, because we're going to convert everything into a string, that's better. And then we're going to add the average reward, and then we add %s as well. Then we're going to close the quote, and then we add a %, and on the other side, we input the variables that are going to be this first %s, that is the epoch here, and this second variable corresponding to the average reward, which we will compute right now. So the average reward variable doesn't exist yet. We're going to create it right now. So we are going to use str epoch. Even if epoch is a number, we will convert that into a string. That's better. And we're going to add str, that's going to be the average reward. And so we're going to create a variable that we're going to call avg reward. And now we're going to create this variable and compute it. Okay, so let's do this. That's the only thing we had to do left. So epoch we already have. Now let's compute average reward, and we need to compute it right here, still in the epoch loop, but out of the batch loop. Because now we have our batch sampled, and we have our training happening in the batch, but now the forward propagation plus the backward propagation is done in the batch, so we are getting back into the epoch loop, and we can now compute the cumulative rewards, which we can do with our nSteps object. Because our nSteps object contains this function, reward steps, that allows us to get the cumulative rewards happening in the steps, during the nSteps run. So we are going to use it right now to update the new rewards of the steps, and then we will update the moving average object by adding the cumulative rewards to the moving average object and then recomputing the average. And that's how we're going to get the average reward. So let's do this. The first thing we need is the rewards that are updated. So let's call them rewards steps. And then, as we said, we take our nSteps object, which was, I remind, created here, an object of the nStep progress class from our experience replay file. So nSteps object, then we add rewards steps, and then some parentheses. All right, so that will get us the new cumulative rewards of the steps. All right, but then we need to add these new cumulative rewards in our moving average object. And to do this, we have a method, this time in the moving average class, which is this add method. So that's very simple. We take our moving average object, which we created here with 100 steps. Then we're going to use our add method, and then in the add method we input our reward steps. And this will add the rewards of the steps into the moving average. All right, and finally we can compute the average reward, and that is, well, that's the same variable here. So that's what is going to be equal to the average reward. And to get it, we just need to use the average method this time from our moving average object, and that is, we do na.average, just like that, because our moving average was already updated with the new reward steps that we just added thanks to the add method. Great, so now we have our average reward, so that will populate here, and this is going to be printed every epoch. So this is going to be very exciting because each epoch we're going to keep track of how the AI is going. We're going to see if the average reward is increasing. And speaking of something exciting, what's very exciting is that I know that it reaches the vest for sure when it reaches 1,500. So what we're going to do now is that if the average reward reaches 1,500, if it's getting higher than 1,500, well, we're going to print something new, and that's going to be the final print, the very successful print. We're going to print that we can say, congratulations to your AI, because your AI wins. So that would be awesome if that happens. If we reach an average reward larger than 1,500, we can be 100% sure that the AI reaches the vest. Maybe it's a little lower than that, but I experimented with 1,000 and sometimes it didn't reach the vest, but with 1,500, if we get there, well, the AI wins for sure. So we're going to watch that afterwards. All right, so that would be very exciting. And then that's actually almost the end of the code. We need to specify that we want to stop the training if that happens. If it reaches the vest, well, it no longer needs to train. So we're going to end all the process with a break. If we reach an average reward of 1,500, we can finish the whole process. And to do this, we can use this break here. All right. And then one last thing to do. When the game finishes, that is when the AI wins, well, we can close the environment. And so I'm adding just one last section here, which I'm going to call closing the Doom environment. So to do this, we take our Doom environment, which we called Doom end, remember? And then we can just add dot close. And that's all. That will just close the environment, which is better to do once you finish the game. All right, so we're done. So I'm so excited to see the results. And actually, I'm going to have a surprise for you in the next tutorial while watching the results. So it's going to be pretty exciting. And so now I guess it's time to play with the AI and have fun. So let's hope we can reach this vest as fast as possible. That's the goal of this Doom environment. All right, so let's have fun. Prepare yourself a good coffee or a good tea. Now it's time to sit comfortably in our chair and watch some very cool videos of our AI playing Doom. So let's do that in the next tutorial, and until then, enjoy AI!